Within Chapter 4, we're looking at different types of reactions that can take place in aqueous solutions. A few different types of reactions are listed: oxidation reduction, precipitation, and neutralization. Neutralization reactions involve acids and bases. Within this video, we're going to look more closely at what makes something an acid or a base, describe them as strong or weak, and connect them back to ideas that we had at the start of the chapter, which includes considerations of things as strong as and weak electrolytes, and also the corresponding particle representations. Strong and weak acids and bases. Understanding those is a lead-in to understanding neutralization reactions. Memorizing information and recognizing strong and weak acids and bases is not an easy skill, but I think it's one that we can develop, and it's an important precursor to understanding these more difficult ideas. A lot of times students have experienced some difficulty when they're trying to connect the different formulas and equations with what's taking place at the particle level for acids and bases. When we first described general properties of aqueous solutions, we had three different classifications: non-electrolytes, weak electrolytes, and strong electrolytes. And we considered the kinds of observations that we would make, which would be, do we have free ions in solution or not? That's what a conductivity probe was describing. When we took molecular substances like water, sugar, methanol, they could dissolve in water, they could become aqueous, but the molecules were preserved. For our strong electrolytes, when those become aqueous, they're producing ions. And we needed to be careful with these ionic compounds to keep track of which ions they were producing. How did they dissociate? Was it a polyatomic anion? Was it the case where we had 2 chloride for every 1 magnesium? Keeping track of how an ionic compound dissociates, an important skill for us. Moving then on to acids and seeing where they fit within this description. Here I have some information from the textbook. We'll be describing acids as substances that ionize in aqueous solution to form H+ ions. If we look within the different formulas here for common acids, hydrochloric acid, nitric acid, sulfuric acid, acetic acid, in some of the examples we have polyatomic anions that we were supposed to have memorized, that we have memorized. So take a second, pause the video. Within these common acids, which polyatomic anions do you recognize? More information on acids. Acids like HCl or nitric acid are called monoprotic acids, whereas sulfuric acid is diprotic. The mono or di is referring to how many protons, how much H+ we get per molecule of acid. HCl, HNO3 are each donating 1 proton. If we look in the formula for sulfuric acid, H2 is corresponding to 2 protons. It's not an H2 molecule. It's 2 protons per molecule of acid. When the sulfuric acid dissociates, it takes place in 2 steps. So here's a description where it's donating the first proton, and then the HSO4- donating the second one. That first equation is describing a strong electrolyte. Sulfuric acid is a strong electrolyte for donating the first proton. That's what that arrow going in one direction is designating. HSO4-, that's a weak electrolyte. With a weak electrolyte, that is being symbolized by these arrows going back and forth in both directions. It's only partially dissociating. We would have all 3 of these in the beaker at the same time. With the sulfuric acid, the H2SO4, I don't think I have any of the H2SO4 remaining. I think it's dissociated into these 2 components. But for a weak electrolyte, I would have all 3 in the beaker at the same time. That's what the back and forth arrows are designating. That's something called equilibrium. Equilibrium is a very big idea in the second semester. It's not very important in this particular class. When I say it's a big idea in the second semester is almost entirely devoted to analyzing examples of equilibrium. In this case, this is, I think, our first real example where we're looking at a weak electrolyte partially dissociating and all of these species then being present in the beaker. At the bottom, we have a description of a common acid, acetic acid. So it's an acid you might have heard of before. It's a primary component in vinegar. We have a formula listed. I show two different figures. Based on that description, would you say acetic acid is best described as monoprotic or tetraprotic? Why do you think it's written CH3COOH? And what questions do you have based on information on this slide? Pause the video. Please respond. Moving on to bases. Our definition for a base is going to be a substance that produces hydroxide ions when they dissolve in water. Common examples are ionic hydroxide compounds. Sodium hydroxide, potassium hydroxide, calcium hydroxide are common bases that we will frequently see. So for these common bases, do you predict they're going to be strong, weak, or non-electrolytes? Pause the video, share your answer, explain your reasoning. To summarize these features right here, what we've been talking about, acids, let's think of those as they ionize in water to produce H+. Sometimes you'll see it also written as what's called the hydronium ion, H3O+. They're going to be equivalent for us. They're giving us protons in solution. Oops, sorry about that. In water, the base is going to be producing hydroxide. Common strong acids and bases that we want to be familiar with. I need you to memorize, if you have not yet done so, these strong acids. There's not very many of them. Please memorize the formula and the name. Also, this description here for strong bases. What happens with a strong acid? Strong acids are strong electrolytes. Here's a general description of how they're going to dissociate, donate the proton, and we'll have the anion remaining. For sulfuric acid, it's a strong acid with respect to losing the first proton. Strong bases, they produce hydroxide. Depending on the formula, they could produce 1 hydroxide per formula unit, 2 hydroxides. Failing to account for the dissociation of a base, like magnesium hydroxide or calcium hydroxide, is an extremely common student error. I'm asking you to stop the video here. Just make a note to yourself. Give some kind of response. Tell me why you are not going to make that error. This is an extremely common error. I need you to pause and recognize when you see a formula like calcium hydroxide, that it will produce 2 hydroxides. Pause the video. Give yourself a reminder. Do something to make it stick so you won't be making that error. So returning to our earlier slide, strong acids, we have how they dissociate. We have the arrow just going in one direction, and the ones that we need to know. For strong bases, this general formula, I'm showing it here with 2 hydroxides. That would be relevant for calcium hydroxide. For sodium, potassium, lithium hydroxide, the formula would be different, so the number of hydroxides it donates would be different as well. How about weak acids? Weak acids are weak electrolytes. They only partially dissociate. HF is a weak acid we want to know. Acetic acid, another weak acid that we need to know. Arrows back and forth showing that it's in equilibrium. It's going to partially dissociate. It would be mainly the acetic acid molecule. It would be mainly the HF molecule. Weak bases? Weak bases will produce hydroxide by reacting with the water. One that I need you to memorize is NH3, ammonia. There's no hydroxide within ammonia. But notice when it's added to the water, it forms the ammonium ion. That's the one polyatomic cation that you need to have memorized, and hydroxide. So the weak base is leading to hydroxide in the water by having reacted with the water. Those are three weak electrolytes I need you to memorize: HF, acetic acid, and ammonia. Two of them are acids, one of them is a base. Students always have trouble remembering that one of these is a weak electrolyte. Which one do you think it is? Out of those three, which ones do students all the time mistake and consider it to be strong? Pause the video, make a prediction. Students always mistake HF, and I get it. We have the others within that same column: HCl, HBr, HI. Why wouldn't HF apply as well? I completely understand the students' error on that point. But let's remember that it is a weak electrolyte. It's a weak acid. In fact, the only strong acids I need you to know are the ones that are listed right here. Every other acid that we encounter is going to be a weak acid. So we can add this to our summary sheet. Weak acids, HF and acetic acid, only partially dissociate. Those are common examples that we'll see. Our weak base that we'll frequently see in examples is ammonia. That's mainly the ammonia molecule. So if we go back to our general properties and add this information, we now have cases of weak electrolytes. Weak acids and weak bases are weak electrolytes. If I add acetic acid, HF, ammonia, they'll be mostly in the molecule form and only some ions produced. Adding to our list of strong electrolytes, strong acids are also strong electrolytes. Nitric acid, HCl, HBr, all strong acids, all strong electrolytes. Here's a question asking you to apply these terms at the particle level. So put these in order or assign them. Rank the acids from the strongest to the weakest and explain your reasoning. Pause the video, share your work. One more question for you. Which of these substances, when dissolved in water, is going to be a strong electrolyte? I'd like you to pause the video. Which one do you think is a strong electrolyte? And in fact, can you classify each of these as a strong, weak, or non-electrolyte? If there's one or more than one that you're unsure of, ask about those.